Okay, Assalamualaikum warahmatullahi wabarakatuh. Today we're going to continue with the single phase half wave control rectifier, and the session outcomes will be after completing this session, the student shall be able to firstly describe the operation of the rectifier, whereby we're going to look into the waveforms, okay, so that you can describe, you can explain the operation of this half wave control rectifier. And then number two will be derive the quantities related to the performance of the rectifier, as what we always do for the rectifier. We're going to look into the output voltage, the average of the output voltage, and so on and so forth. And then number three, solve problems related to the rectifier. We're going to have a few problems, and then we try to solve it and try to get the answer for that. And finally, simulate the circuits using PCM. I'm also going to share with you how to simulate the circuits, very basic circuits of the control rectifier, and then you will, inshallah, will be able to simulate by yourself. Okay, before we go into the control rectifier, let's have a look at the model graph. So if you see, this model graph actually comes with this document map, we call this. So you can click whichever chapter, whichever point that you want to go uh, using this document map. We call this a document map or bookmarks. Right. So firstly, let's go back to the block diagram of a complete power electronic system. We know that this is a complete block diagram of power electronic system, whereby we know that the power electronics converters actually utilize the switching the semiconductor devices, power semiconductor devices, to control the input to the output, right? So the input can be from AC to DC, can be AC DC, and it is unregulated, which means you cannot regulate, you cannot control the input source. It may the input is actually from the DMB, if you can say that, from the DMB, and it is subjected to noise, subjected to the disturbance, over voltage, voltage sag, voltage swell. Okay, so this is unregulated, you cannot control it. And then we have on the right hand side here, we have the load, which is the output. The load requires a certain output voltage and current in the form of AC and DC. And of course, normally, regularly, always the load wants a stable input to itself. You want a stable uh, input voltage to the load. So you must regulate, you must control the voltage that will be supplied to load. Uh, so therefore, you must have this controller in the circuit, isn't it? So that you can regulate the output voltage of power electronic. Without this controller, you won't be able to control the output of the converters. And when we look into these power electronic converters, there are uncontrolled. We have covered the uncontrolled in the chapter 4 here. We have covered the uncontrolled rectifier, whereby we utilize the diode. So we know that the diode only always depend on the voltage and current of the circuit to be turned on. So you cannot control the output voltage here, isn't it? All right. So therefore, in order for you to provide a stable output voltage to the load, for example, your laptop, which needs a 90 volt DC, your phone, your mobile phone needs a 5 volt, so on and so forth. Then, so you must have a control rectifier, right? So you have to have a control rectifier so that you can have a external mechanism, external control parameter that can change the output voltage in the presence of the disturbance on the input side. So if you see that the input is raised by a few volt, for example, from 240 volt to 245 volt, of course, if you talk about if nothing has been done, which means you don't have a control, the output also increase to a few percentage, isn't it? So you must bring it down again. So you must have a control rectifier. So today, this session, we're going to continue with the control rectifier of a single phase. So we have a few sections. The first one we're going to be introduction, and then we're going to look into the single phase half wave control rectifier, and then we extend to single phase full wave control rectifier, and finally we also going to look at the inverter operations. Okay, so in terms of inverter operation, regular in normal operation of a converter of a rectifier, the power actually flows from the input side to the output side. So the power flow is from the input side to the output. This is under rectifier operation. But under certain conditions, you may see the power flow which is from the output to the input. So that will be discussed in this inverter operation of the rectifier. Right, so now let's start with the uncontrolled rectifier, just to refresh yourself on the uncontrolled rectifier. So I'm going to click here and then go to the first circuit, which is half wave uncontrolled rectifier. So I believe most of you know how to describe the operations now. Again, to explain the circuit operation, you always look into the supply voltage. You always make the supply voltage as a reference for you to describe your circuit operation. So we have a positive half cycle, and then we have a negative half cycle, isn't it? So for the first positive cycle, the diode will be forward biased and current start to flow in the direction of the diode, and therefore diode will be turned on, and when this is turned on, it will appear as a short circuit, isn't it? So whenever it's a short circuit, then VDC equals to VS. It will follow exactly the supply voltage. Okay? And then during negative half cycle, it will be turned off, and therefore there will be no current flow. So when there is no current flow, there will be a zero voltage across your R, isn't it? So that's why on this negative half cycle, during negative half cycle, there is a zero voltage there. Okay, so that is diode operation. What about if you change the diode? You're going to remove this and replace with a thyristor. Okay, so thyristor, it has the gate, right? So it will replace by, you have a gate terminals here. Okay, so you have a gate terminal whereby this gate terminal actually will control the turn on of the thyristors. So what you need to do now is actually, the waveform is very much similar to the uncontrolled rectifier, but you need to modify the turn on of the thyristors. Okay, because the gate signal will allow, from that gate signal will instruct the thyristor to be turned on at any time during the cycles. Okay, so now let's start with the first control rectifier. You can read this, right? And then single phase half wave control rectifier. So now we look into the single phase half wave control rectifier, whereby you have this now the thyristors. Okay, and this is the gate signal. So what is this 4546? 4546 actually define the alpha angle, right? Alpha is the firing angle, or sometimes we call this as a triggering angles. You trigger the thyristor, you instruct the thyristor to be turned on. Okay, so for example, in this example, we have this alpha equals to 45 degree. And what is this 46? We have 45 is the alpha, and then we have 46 here. 46 means that you're going to give a short pulse, right? You're going to give a short pulse to the gate signals, to the gate terminal, whereby it consists of 45 degree and 46 degree. This is the minimum pulse. You can have also 45 to 47, which is defined as a short pulse. If it's a long pulse, it will be 45 to 180 degree. This is known as long pulse gate signals. Okay, so for thyristor, it is sufficient. It is enough for you to give a short pulse to the thyristors here. Okay, so in PCM you will need to define 45. Need to define this figure, this number 45 and 46. Okay, so let's have a look at the waveform. So we know that our alpha is 45 degree. So therefore, during positive half cycle, this is the positive cycle of the supply voltage. The thyristor will experience a forward bias, but it will not be turned on yet because it waits for the firing angle. It needs a pulse to the gate signals, therefore then it will start. So in this case, we have alpha equals to 45 degree. So this is from there to there is 45 degree. So just after 45 degree, then the thyristors will be turned on, and therefore you're going to see that it will appear as a short circuit. Okay, after 45 degree, it will appear as a short circuit there, and therefore VDC will be equals to Vs again, and at the waveform you're going to see now it will follow the output voltage just after 45 degree. So the red waveform there represents the output voltage, and this is the voltage, and the bottom waveform here is for the resistors. Okay, so now if you look at the waveform, there will be a new variable in your circuit, in your waveforms, which is alpha, isn't it? So before this we have 0 to pi. Now it starts with alpha, then it ends at pi degree. So to get the output voltage, what you do is you just integrate. This is the general equation. I'll always stress on the remembering or understand the general equation. So this always be the general equation. It applies to any waveform. Okay, so when after you know that and it is convenient to change. This is general equation in time domain, and then you can change that into radian. Is that it? So if in the radian, this will become 2 pi and pi, isn't it? Wait. So this will become 2 pi in radian. This will become 2 pi, and that also 2 pi. Okay, so this still the general equation in terms of radian. So now when you try to evaluate the waveform, then you look into the waveform, and the waveform, now the limits of the waveform change from alpha to pi, because now you only refer to that output voltage, control output voltage waveforms, whereby the voltage only exists from alpha to pi. And that's why you have the limit of alpha to pi, v peak sine theta d theta. And solve that, and then you find out that the output voltage now becomes VDC equals to V peak, or divide by 2 pi 1 plus cos alpha. So if you compare this 5.1 with the uncontrolled versions, this is I can go to the uncontrolled half wave rectifier. So this is the equation for the uncontrolled 4.1 here, which is V peak over pi, and for the control rectifier resistive load, this will be the equation. V peak over 2 pi 1 plus cos alpha. Okay, all right. So therefore, if you look at the output voltage equation, now there is a external or extra parameter, which is alpha here. So if you vary the alpha value, you will get different output voltage, isn't it? So if you vary the alpha, you will get a different output voltage. So you look at the area of the output voltage, sorry, look at the area of the output voltage, of course it will change. If you have alpha equals to 0, So if you have alpha equals to 0, which means it will operate as a diode, isn't it? The output voltage waveform will be exactly as the output for the diode rectifier. So it will start from there. But if you start to have an alpha from whatever value is until pi, then the area under the curve will be smaller and smaller, getting smaller and smaller. So if you increase alpha to that point, so this is your area, and then if you move further alpha to that point, then you have a smaller. This will be your voltage waveform. So your output voltage will become smaller and smaller as you increase the value of alpha here. And alpha maximum is actually at pi. You can have alpha equals to pi, then the output voltage will be 0, isn't it? So if you have alpha equals to pi, then the output voltage will be 0. You can check with the equation here. Okay, so now we will move to the resistive and inductive load. So again, we go back to the resistive and inductive load for the diode operation. Resistive and inductive load. Yeah, right. So go back. This is the output voltage waveform. So I hope you still remember how to explain it. So you understand how to explain the circuit. Why we have a beta? Beta is the extinction angle. This is where current goes to 0. Current goes to 0 because of this L. When we have L, there is a stored energy, so the current cannot change direction instantaneously. It won't change direction instantaneously. So therefore, we still have current, even though your voltage is already at negative, but we still have a positive current flowing. There, isn't it? We still have a positive current flow. So that turn on the diode. And the output voltage will still copy the output voltage until you have current equals to 0. So this is the diode operation. So again, for control rectifier, what we need to understand that we control the input side, the turn on time. So we have now an extra parameter again, alpha here, and then we still have beta. This is where current goes to 0, alpha and beta here, isn't it? So therefore, you must have this. You need to have the output voltage, the average of the output voltage. So you consider from alpha until beta here, and that's why your voltage waveform, your integral, the limit of the integration here will be from alpha to beta, right? Okay, so then you have this equation, and then you can try yourself and try to solve for this equation. You just refer to the previous section on how to obtain the current. You must consider we'll consider force response and also the natural response of the circuit, and you will get this waveform, this equation of the current. Okay? So how to get beta? You must equate this equals to 0. You must equate this equation into 0. Alright, so you have alpha beta equals to 0. So you replace the theta here, every theta that you have in your circuit with beta, and then you use the calculator and set to 0, then you will get the beta. And again, remember we have this initial condition in your calculator, isn't it? So you must set your initial condition, and if you look at the circuit here, your initial condition should be more than 180 degree, which is more than pi, because your beta here is closer to the pi value, isn't it? This is pi here, so beta is closer to the pi. Don't let the equation in your calculator here, don't let it, the initial condition equals to 0, because if you set your initial condition to 0, you will get the value of alpha. But if you you set your calculator to the initial condition equals to pi, then you will get to the beta. Okay, right. So now we proceed with the resistive and inductive load with freewheeling diode. So why we need this freewheeling diode? This is known as freewheeling diode, whereby you're going to replace, you want to you want to place a diode in parallel with your load. So why we need that? And this is because if you look at the circuit without, the original circuit of the half wave control rectifier without this diode here, you're going to see that there is a negative. Come back to the, okay. So if you look at this waveform, there is a negative area here, isn't it? There is always a negative area. Okay, so this negative area will actually reduce the output voltage, the total output voltage, the average of the output voltage, isn't it? Because of this negative area. So it is good for us if we can remove this. Okay, we're going to remove that negative, so therefore there's only a positive area, and therefore there will be a more output voltage available from the half wave rectifier. So the target is to remove, the objective is to remove this negative area. So that's why we introduce this freewheeling diode, whereby you're going to put it in parallel with your R plus and with your load. Right, so let's look at what happens during the circuit operation of this the half wave rectifier freewheeling diode. So again, for positive half cycle, during positive half cycle, the very similar operation, the thyristor will experience a forward bias, and then we're going to wait for alpha. The thyristor will wait for the firing angle, and then it will start to turn on. And then, okay, during negative half cycle, when it goes into the negative half cycles here, but before that, so when thyristor before that, okay, let's explain again. So when we trigger alpha, we trigger the thyristor at alpha, then the thyristor starts to turn on, and it will appear as a short circuit, and therefore this diode will be reverse bias, isn't it? Because of a positive negative of your anode and cathode here, and therefore it will be reverse bias, and there is a current flow will start to flow in that direction. So you bypass this diode. So the normal operation of the control rectifier, so we're going to see that output voltage waveform, and then until the negative half cycle, when it goes to the negative half cycle, we can see that the current is still flowing. This is the output current, right? This is the output current, which is continuous. Look at the current, continuous, whereby it doesn't drop to 0. This is 0 levels, doesn't drop to 0, isn't it? So this current is known as a continuous current. It always flow in the output voltage, output side here. So this will be your current. Current always flow in this output side, a continuous current flow. Right, so it always flow in the output side. So therefore, during negative half cycle, when the voltage goes to negative half cycle, the current now, instead of flowing through that path, it will start to move into the diode, right? Because your supply here is now the negative voltage, so there will be a more positive, the diode now become more positive, which is forward bias, and we also have this current now, instead of flowing through the back to the input, now it will flow through the diode, forcing this diode to turned on. So whenever this is turned on, it will appear as a the diode will appear as a short circuit, isn't it? So the diode will appear as a short circuit, and therefore the voltage here will be a voltage drop across a short circuit will always be 0, and that's why during negative half cycle the diode turn on, and therefore the output voltage becomes 0. So instead of we have a negative voltage just now without the freewheeling diode, we have a negative voltage here, isn't it? So that negative voltage actually reduce the available output voltage, and therefore with this freewheeling diode, this area has been removed. Now we have more positive. So if you look at the total output voltage, there will be a more positive area, and therefore you increase the available output voltage from this rectifier. So this is the purpose of freewheeling diode. Okay, you can read again, and um, and therefore your output voltage now becomes same as the first equation that we have, v peak over 2 pi 1 plus cos alpha. And therefore there is some notes here. Advantage: increased average load voltage. Of course, in the even though we have R plus L condition load, but we still have the output voltage more, right, increase or very much similar to the R load, which is V peak of 2 pi 1 plus cos alpha. But the disadvantage is, if you look at the supply current, it becomes sharp edges. What does it mean is that it will jump, the current will jump from almost peak value, this is peak value here, to 0. Okay? So there will be a high di over dt, isn't it? The rate of change very high. You can also uh, make an analogy whereby if you jump from first floor, okay, uh, you imagine that you are on the first floor and then you jump to the ground floor, compared to you jump from the fourth floor to the ground floor. Of course, you suffer from the diode, the thyristor will suffer more if you jump from this peak, almost peak value to 0. So that is really the disadvantage of having this uh, uh, what we call it, a freewheeling diode, or sometimes we call it a flywheel diode, FWD. Okay, so we continue with this resistive and inductive load with freewheeling diode and back EMF. So the same circuit, a half wave rectifier. Now we add the back EMF. So again, why we have this back EMF? Because it's due to the DC motor operation. We drive this DC motor operation, then that's why we have this back EMF in the output side together with the R plus F. Okay, so before we start, we'll look at the current. If you look at the current, because of that, be at back EMF, without the back EMF, be a back EMF, just now, we see that the output current always flow in this output side, isn't it? Because of continuous output current. But because of that back EMF, it opposes. Look at this polarity of back EMF. It's always opposed to the flow of the current, isn't it? And therefore, the current will dies off, and then it become discontinuous. So if you look at the red current here, it is discontinuous, whereby the current now goes to 0 instead of the uh, continuous operation as before. This is continuous operation because of you add the back EMF at the output side here, plus minus, and therefore it opposes the current, and it will actually force the current to goes to 0. Okay, so now to explain the circuit, we always start with the 0 volt, the supply voltage for the positive half cycle. So at the beginning of the uh, operation, look at the beginning of at this point. Okay, so during this point again, because thyristor experiences forward bias because of that supply voltage positive. It is forward bias, but now it still wait for the alpha to be, the thyristor to be triggered, and therefore just after you have alpha, but you must make sure that alpha is beyond this intersection between back EMF and the supply voltage. Why? Because if you trigger the thyristor before this intersection, okay, because the basic, the fundamental is that Vs should be higher than the back EMF, isn't it? For to be able for the current to flow through that side, we must have Vs greater than, must be greater than VDC or the back EMF, isn't it? Then you will have a power flow, the current start to flow from the supply to back EMF. So you must wait until supply voltage go beyond the back EMF. So this is back EMF, I call it so E. So you must wait the supply voltage to increase just after your E. Then you can start to have the trigger the thyristors. If you trigger thyristor below that, then you won't see any current flow. The diode will not be turned on, right? So, okay. Okay, so let's say we have alpha beyond this intersection between VDC and VS. So when we start to have the firing angle, then the current builds up, and now you have again this will appear as a short circuit, and therefore VDC equals to VS, and this is turned off because of reverse bias, and now we see that the output voltage equals to the supply voltage. And before that, okay, sorry, before that, there is no current flow, isn't it? There is no current flow, and thyristors will be off. So, and also this is off, right? So the current also off because there is no current flow here. Current is 0, I is 0, and therefore VDC will be equals to back EMF. So that's why you see that the VDC equals to VF. Okay? So the output voltage, sorry, this is at the beginning, VDC equals to back EMF. So this is your output voltage equals to back EMF until you start to trigger alpha. Okay? So when you trigger alpha, then the voltage equals to supply voltage again until the negative half cycles. Again, when the currents start to flow in that direction through the freewheeling diode, and therefore the diode will be turned on and it will appear as a short circuit, and therefore voltage and current, sorry, if you measure that point, the VDC will be 0, isn't it? Okay, so that's why you have 0 voltage until the current goes to 0. Okay, when current goes to 0, there is no circuit, there is no current flow. This is also open circuit, and therefore there will be a voltage of VDC equals to back EMF again. And so that's why you have this back EMF. Right? So this is your output voltage again. We are still interested in looking at the average value. So you must integrate from 0 to 2 pi. So you must integrate from 0 to 2 pi. So now you have 3 area. Integration is the area under the curve. So you have one area here, and then the area of under the curve from alpha to beta, and then you have another area. We have area 1, area 2, and area 3 here. Okay, so therefore, if you look at the derivation, integrate the one cycle, and this is in radian, 1 over 2 pi, 0 to 2 pi, and now you start to look into the waveform. You have area 1, sorry, and then you have alpha to pi. So look at this waveform. It is alpha to pi, isn't it? So your waveform only exists from alpha to pi, not to beta, because it only exists from this point until 0 here, isn't it? Pi. So this is pi, so that's why the limit is from 0 to pi. Okay, that's why the limit is pi here. And then the V peak sine theta, this is area, and therefore VDC equals 1 to 5. So you have to memorize this question, or you want to derive if you want to. But of course, you need to fill the gaps, and therefore you have this 1.5. Right, so some notes. Back EMF forces DC current to go to 0, discontinuous operations. Okay, so now we're going to continue. Alright, so that is the first section of the single phase half wave control rectifier.